Hi friends, today we will learn propositional equivalences with you. Sorry for my voice, I'm a little bit sick today. Okay, let's start. Propositional equivalences. This is about discrete mathematics. We begin our discussion with a classification of compound propositions according to their possible truth values. Okay, so a compound proposition that is always true, no matter what the truth values of the propositions that occur in it, it's a tautology. Okay, if a proposition is always true, it's a tautology. A compound proposition that is always false is called a contradiction. And a compound proposition that is neither true, neither tautology nor a contradiction. This means that it can be true or it can be false. Okay, and this is called contingency. So, examples of a tautology and a contradiction. We know that P disjunction negation P is always true. Yes, if P is true, then negation P is false, as you see from the slide. If P is true, the negation P is false. And the disjunction of P and negation P is always true because what is the definition of disjunction? If one of the statements is true, then our result is true. And if P is false, then negation P is true. It means that again one of the substatements is true, so hence our result is true. So the disjunction of P and negation P is always true. It's a tautology. What is contradiction? The conjunction of P and negation P. If P is true, the negation P is then false. And we say that the conjunction means and. And if both two substatements are true, then our conjunction is true. Otherwise, it's false. Here, our first statement is true, the second is false, or first is false, the second negation is true. One of them is false, therefore our result is always false. So the disjunction of P and negation P is a contradiction. Let's continue. Logical equivalences. Definition. The compound propositions P and Q are called logically equivalent if the biconditional between them is a tautology. Okay, the notation, look, this notation denotes that P and Q are logically equivalent. Let's see the table. Here is the De Morgan laws. Here we show that the conjunction of PQ is in the brace, and behind this brace it's a negation. If we use De Morgan's law, both two substatements will be negation P and Q, and the conjunction will change, it will be disjunction. Again, in the second row, here is the disjunction, and at the end, disjunction changed and became conjunction. So the compound propositions P and Q are called logically equivalent if biconditional statement between them is a tautology. Okay. Example, show that negation P disjunction Q and negation P conjunction negation Q are logically equivalent. Here is the example. We have substatements P and Q, and negation P. Firstly, we construct the negation P, then negation Q. Here is P 0011. You see in this column. The negation P is 1100. You see? And what about Q? 0101, and the negation Q is 1010. Okay, 0 became 1, 1 became 0, and etc. And if we want to find the disjunction between these two statements, we know that 00 is always 0. By the way, we used Boolean numbers, yes, 0 and 1. We don't use true and false. We just will use 0 and 1, okay? We said that if one of the statements is true, so the disjunction between them is always true. And here, the disjunction between them is always true. What about the negation of this operation? 0 became 1, and all ones became 0. So our final result is here, yes? Now we find the first operation. Let's find out the result of the second operation. Look, please. We should find the conjunction of negation P and negation Q. Look, the conjunction of 1, 1 is 1. Otherwise, here we have 0, 0, and both of them are 0. So the conjunction between them will give us 0. Okay? You see, these two operations are the same. The result, the trust values of these two operations are the same. So we proved that negation P disjunction Q and negation P conjunction negation Q are logically equivalent. It means that their results are all the same. Another example, show that P disjunction in the brace Q conjunction R and P disjunction Q conjunction P disjunction R are logically equivalent. This is the distributive law of disjunction over conjunction, okay? And let's find out. You see, here we firstly wrote the trust values of P, Q, and R. Look at the structure, please. What about P? First, 4 elements of P, first 4 trust values of P are 0. Then, second 4 trust values are 1. Okay, for 0 and for 1. What about Q? Here, 2, 0, 2, 1. Again, 2, 0, 2, 1. And what about R? Here we have 1, 0, 1, 1, 0, 1, and it keeps going. Okay, 4, 0, 4, 1 in the first column. In the second column, 2, 0, 2, 1, 2, 0, 2, 1. And in the third column, 1, 0, 1, 1, 1, 0, 1, 1. Okay, this is the structure of two substatements. If we want to construct the trust values, trust table of three substatements, firstly we should write this structure, then we continue our operations. Okay, so let's continue. Here the conjunction of between Q and R. Here Q and R. We want to find the conjunction. 0, 0 is 0. 0, 1 also. 1, 1, the conjunction between 1, 1 is 1. You see here. Again, 0, 0, 0, and the conjunction between 1, 1 is again 1. So this is our first operation. What about the second? We want to find the disjunction of P or conjunction. Okay, here, this one, and let me change the color and continue. So, we want to find the connection between these two operators. So 0, 0 is 0. Okay, 0, disjunction 0 is always 0. This is always 0, again 0, but we state that if one of the subsegment is true, our result will be true. So 0, 1 will give us 1. And again, 1, 0, 1, 0, 1, 0, and 1, 0 gave us this column. Yes, our first three trust values are 0. The others are true, 1. This is our first this is our first result. We find out this one, and next we want to find this. Okay, let me here firstly we should find the trust values of this first brace. P disjunction Q. 0, 0 is 0, 0, 0, again 0. You see, here is the result. 0, 0. 0, 1, 0, 1, 1, 1, 1, 1. In all other two substatements, we have between them we have 1, a point 1. One of these points is 0 and the other is 1. And if we remember the definition of disjunction, we know that if one of the trust values is true or is 1, our result will be true or 1. So here all the results are 1. Okay. What about the second brace? P disjunction R. This is P and R. This is 0. This is 1. Yes, here. Again, 0, 1. Yes, and all others are 1 because 1 take place here. And what about conjunction between these two braces? Conjunction. 0, 0 is 0. 0, 1 conjunction 0. 1, 0 conjunction 0. All these are 1 and the result is always 1. So look at these two results. You see they are the same. Yes, so the trust values of these operations are the same. So these two operations are logically equivalent. We use distributive law and find out that they are equivalent. Let's continue. If you have any question, please let me know by writing your question below in the comment. So constructing new logical equivalences. Example, show that the negation of P implication Q and P conjunction negation Q are logically equivalent. We now don't use the trust table, okay? Here, we just open the braces. Okay. Here, look at this. P implication Q. In our previous slide, we proved that P implication Q is equal to negation P disjunction Q. You can watch this video. I will add it. Okay, they are logically equivalent. Yes, we write negation P disjunction Q instead of P implication Q. Here we write again negation. It remains the same. Negation P disjunction Q, and we open the brace using distributive law. So negation P, our disjunction will be, the negation of disjunction will be conjunction, and the negation of Q. The double negation of P is equal to P itself, and the conjunction remains the same, and here is the negation Q. So we find out that these two operations are logically equivalent. And let's continue. Show that negation brace P disjunction again brace negation P conjunction Q and negation P conjunction negation Q are logically equivalent by developing a series of logical equivalences. So here is the solution. Firstly, we will use one of the equivalences in table 6, but I will mention table 6 at the end of this slide, okay? And starting with negation P disjunction, negation P conjunction Q, and ending with a negation P conjunction negation Q. Not, we could also easily establish this equivalence using a trust table, but here we don't use a trust table. We just want to develop a series of logical equivalences. So here we use the second De Morgan law and negation P. This will change. The disjunction will be the conjunction and negation this brace. Okay, negation this brace. This brace will remain the same. Okay, here is the first De Morgan law. Negation P, we open the brace here, the double negation P, the conjunction will change and be disjunction, Q, change and be negation Q. Okay, so we know that double negation of P is P itself. So we write negation P conjunction, P disjunction negation P. This is by the double negation law, and by the second distributive law we use negation P conjunction P here. Okay, negation P conjunction P. Disjunction negation P conjunction negation Q. We know that negation P conjunction P is always contradiction. This is always false. Yes, because this rule, it's contradiction. And if we find the disjunction between the contradiction and this operator, we can write it like that. Negation P, we can change. Yes, we can change the order by the commutative law for disjunction, and we write negation P conjunction negation Q by the identity law for false, for contradiction. Consequently, we find out that these two operations are logically equivalent. Yes, we find this. Okay, again, if something is unclear for you, please let me know. Let's continue. Show that P conjunction Q implication P disjunction Q is a tautology. It means that our result should be true. Yes, the trust table, the last column in the trust table should be true, 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 true. Yes, all the trust values should be true. Or if we want to use logical equivalences to demonstrate that, we should find in the end true. Let's start. So again, in our previous video, we said that let it be, oh, sorry, okay. Okay, let it be A, okay, and let it be B. We said that A implication B is logically equivalent to what? Negation A, yes, negation A, conjunction B. Let's find out the negation of A. We write the negation in front of A, and this junction between them it remains the same. We use this, okay? We use this formula. And again, here we use the first De Morgan law. We open the brace. Negation P here, negation P, disjunction negation Q. Disjunction remains the same again, and it will also remain the same. By the associative and commutative law for disjunction, we use that. We changed, yes, here we changed negation Q and P. We write that, let me write, negation P, disjunction P, again disjunction, negation Q, disjunction Q. We changed the order because all the operations are disjunction, are the same, so we can change by using the commutative laws and the associative laws. So negation P, conjunction negation Q is always true. It's a tautology. And negation Q, disjunction negation Q, disjunction Q is again always true. We proved it in our previous slide. Okay, and the disjunction between true and true is always true. So we use the domination law and find out that this operation is always tautology. Okay. Is it clear? Do you have any question? Please let me know. And I think that is all. Yes. And thank you for your attendance. Please let me know if you have any question. Bye-bye.